Applications of aqueous equilibria, Chapter 15. So the first part of this chapter deals with buffer solutions, and the second part deals with solubility. Solutions that contain both a weak acid and its conjugate base, or a weak base and its conjugate acid, are known as buffer solutions. And the reason for this is we can basically apply Le Chatelier's principle. So we can look at the way an equilibrium position shifts based on whether or not we've added some weak acid or we've added some weak base. And in this particular equation, we're looking at hydrocyanic acid and its conjugate base, the cyanide ion. So what happens if we add what's called a common ion? Well, the common ion that we would add in this solution would be Cn minus. But we can't just add ions because ions aren't available. They are always bonded to something else in an anionic compound. So we would add sodium cyanide. So how does this shift? Well, we've added a product, which means that the Cn minus would react with whatever acid was present and shift to form water and some weak acid. So if we have strong acid in solution, our weak base would neutralize it. And instead of creating more strong acid, as in an H3O+, we would produce the weak acid HCN. So we're only increasing the amount of this weak acid, which we know then, when it reacts with water, would only produce a small, tiny, tiny amount of H3O+. So a buffered solution will resist a drastic change in pH. There will be a change in pH, but it will be a very small change. So you add strong acid, and the pH will only decrease by a small amount. If you add a strong base, the pH would only increase by a small amount. And once again, a buffered solution would contain effectively an acid-base conjugate pair that is derived from a weak acid or a weak base. So we cannot use strong acids and strong bases typically, because once they dissociate, that strong, the meaning of strong is that there's a complete dissociation. It's an arrow that points one way, and we never go back the other way. So we want something that will react to form product, and the products can react to form reactants. When dealing with these types of problems mathematically, we have to do the stoichiometry first, which is basically just saying how many moles of strong acid have we added, or how many moles of strong base have we added. That reaction will go to completion effectively, because that's what strong acids and strong bases do. Once we've figured out then how many moles we have left over, we can deal then with an equilibrium problem by setting up our ice table. So what are some characteristics of buffered solutions? They generally will contain large amounts of our weak acid and corresponding conjugate base, or vice versa. When we add a strong acid, H+ or H3O+, right, protons or hydroniums, goes to completion, it will react with the conjugate base. Conversely, if we add strong base, hydroxide ions, any of our soluble group 1 metal hydroxides or those few group 2 metal hydroxides, they react completely with the weak acid that is present. So then really we're just looking at a shift. We're either increasing the amount of our conjugate base, or we're increasing the amount of our weak acid that's in solution. So your pH remains fairly constant as long as our concentrations of our original buffer materials, right, weak acid, conjugate base, weak base, conjugate acid, are large compared with the amounts of the strong acid or the strong base that are added. If you add more than what our buffering capacity allows, then we would actually see a drastic change in pH. So basically what happens is we can absorb only so much strong acid or strong base based on what we start with. What are our original concentrations and volumes of our weak acid base pair? So I mentioned buffering capacity. So it's basically the amount of protons or hydroxide ions that the buffer can absorb without changing the pH drastically. And it's determined by the magnitudes of our concentration of our weak acid and our weak base that are present in solution. So the bigger the amount that we start with, the bigger the buffering capacity. So large capacity equals large concentrations. And we see an optimal amount of buffering when our concentrations of our weak acid and our weak base are equal. If they're not equal, let's say we had 2 times as much weak acid than we have base. Well, then that buffer solution would be better at buffering against a base. If we had 2 times the amount of base present than what we had a weak acid, then that solution would be better buffering against the addition of a strong acid. Hence why, if we have equal concentrations, we are a good buffer against both acids and bases. So the pKa of the weak acid to be used in the buffer should be as close as possible to the desired pH. So we use buffered solutions for specific reactions, and if we're looking at a typical pH range, then we're going to want to select that acid-base pair where the pKa would equal the pH. And keep in mind the little p here just means that we're going to take the negative log. So we take the negative log of the Ka, pKa, take the negative log of the H plus concentration, pH. So pKa can equal the pH. And this is only true. pKa will only equal the pH when your HA equals your A minus. So solving problems. Mathematically, we start with our original buffered solution. And we can look at, we're adding acid or strong base. Step 1, we do our stoichiometry. So we react to completion, however many moles of acid or base that we've added. And this is by molar, or sorry, not by molar, not by concentration, but by the number of moles. So we'll look at what is the concentration of acid, how many milliliters have we added. And in this chapter, we're actually going to use millimoles because it's just much easier. If you can take milliliters times the molarity, we can use millimoles. It works out the same way, and I will show you how that mathematical calculation is in class. So we do the stoichiometry, and then we can look at the equilibrium calculations. Once again, equilibrium calculations deal with setting up ice tables. And then this gives us a ratio of our weak acid to conjugate base that then we can look at the modified pH. So specifically, what happens when we add a strong base? So we look at our original pH, our original buffer pH. We add our OH minus, which is our strong base, and all of those OH minus ions that we add to our solution are replaced by our conjugate base. So our weak acid reacts with the hydroxide ions to produce water and conjugate base, which then our pH will only increase by a small amount. Hence why our final pH is close to our original. So looking at these ratios, once again, we're just looking at studying hydroxide. We can do the same thing for looking at adding hydronium ions or strong acid. We have an original ratio, HA to A minus. We want those to be equal to have the best buffer. So when we've added our OH minus, we react the HA to change it to A minus, but the original ratio, it doesn't change significantly, and that's the whole point of having a buffer solution. So our concentration of HA and A minus the concentration of HA and A minus are large compared to the concentration of OH minus that was added. This has been neutralized. So all we've really done is change some HA into some A minus. So how does that affect our overall ratio? Well, that means that this number has gone down and this number has gone up. So we have a fraction here where we're decreasing the amount of that fraction. And the best way to solve for pH in looking at buffering solutions is to use the Henderson-Hasselbalch equation. So we have the pH equals the pKa plus the log of our A minus over our HA concentrations here. This equation is simply derived from looking at any equilibrium expression involving a weak acid. Mathematically, we can take the negative log of both sides. We do some rearranging, and this is how this equation is derived. I can show you how we do that if you're interested. So for a particular buffering system, once again, conjugate acid-base pair. This is buffer, buffer, buffer. Acid-base pairs of weaks. All solutions that have the same ratio of A minus to HA will have the same pH. So what do we mean by this? Regardless of what acid we use, let's say we use acetic acid, or I shouldn't say regardless of what acid, regardless of the concentrations that we start with. If we're looking at acetic acid and we start with a 1 to 2, no matter what the concentrations are, 1 to 2 here is going to give you the same pH because we're looking at the same acid using the same Ka. So 2 molar to 4 molar, 1 molar to 2 molar, 3 molar to 6 molar. It's going to give you the same pH because the ratio is the same. And as I had stated before, if A minus equals HA, our concentrations, this becomes 1, the log of 1 is 0, hence pH equals pKa. So if we have equimolar, or yes, if we have equimolar solutions, then our pH equals our pKa. So how does the Henderson-Hasselbalch equation work? Here is an equilibrium equation that shows a weak acid dissociating into the proton and its conjugate base. So here's where we start. If we add H+, we're adding acid. So the acid cannot react with the acid that's already present. The acid reacts with the base. H+ plus X minus gives us HX, which is why we see an increase in our concentration of our weak acid, a decrease in the amount of X minus that is present, because these things are in equilibrium with each other. One goes up, one goes down. Conversely, if we add OH minus, this is a strong base. Minus cannot react with the minus. Remember, same charges repel each other. Same reason why our H plus is not going to react with our HX. There's nowhere for it to go. So O minus reacts with HX, acid plus base gives us water, and the conjugate base of X minus. So this has gone down because it's reacted with the OH minus. When it has reacted, then it is increasing the amount of X minus, or conjugate base, that is present in solution. Keep in mind, if we did not have a buffer solution and we added strong acid, the acid reacts with the water to produce only hydronium ions, which means that we see a significant decrease in our pH. We go from a pH of neutral, which is 7, to down to 2. Or if we add strong base, we are only producing hydroxide ions, so we see a pH of 7, bump up to a pH of 12. Well, if you start with a weak acid base pair in solution, let's say the pKa is 4.94. We would only see a small decrease by adding acid. Let's say it only drops to 4.74. Or when we add our strong base, it only bumps up to 5.14. So that is the difference between adding a strong acid and strong base to water versus adding a strong acid or strong base to a buffer solution. So this is really going to be the fun part of this chapter mathematically, because we're going to do ice tables and Henderson-Hasselbalchs for days and looking at titrations and pH curves. So we plot the pH of the solution versus the amount of titrant added. So keep in mind, titrant is, when we do a titration, that is what you put into the burette. Regardless of the titration that you're doing, strong acid, weak base, or strong base, weak acid, your equivalence point, stoichiometric point, is when the moles of acid that you've added is equal to the moles of base, or the moles of base that you've added are equal to the moles of acid that are present in your initial solution. So that is the equivalence point. Equivalence, moles is equal to moles, acid to base. So we will look at 3 different types of titrations. One is when you have strong acid and strong bases. Regardless of whether you're starting with a strong acid or a strong base in your flask, your pH at the equivalence point will always be neutral. And that is because they are strong acids and strong bases. It means that we are not producing anything in the solution that can potentially then react with water to create hydronium ions or hydroxide ions. So that's different than what we see with weak acids and weak bases, because they have the power to do that because they go back and forth. So at the equivalence point, your moles of your OH minus equal the moles of your H3O plus. We have completely neutralized whatever we've started with. So in this example, we are titrating 50 milliliters of 0.200 molar nitric acid with 0.100 molar sodium hydroxide. So this is in your burette, and the nitric acid is in your flask. So initially, when we have not added any base, we see that the pH is maybe about 1. As we add the base, we see a slight increase in the pH. And then as we get closer and closer to the pH point, or to the equivalence point, we see a really significant slope here, and then it levels off as we add more base. So equivalence point, moles of acid equals the moles of our base. When you are dealing with strong acids and strong bases, the pH is always equal to 7. So just the opposite here, we're actually starting with our base in our flask, and we have acid in our burette. So when we do that, we're starting with a basic solution, pH of 14. As we titrate, we see a small change in the pH with addition of our acid, and then we see this huge change. We hit our equivalence point at a pH of 7, and then we drop off significantly, because after this pH is 7, after we've reached the equivalence point, there's no more base to absorb any acid. So we see this huge drop then in the pH, because then the only thing that's present is your acid that reacts with water, and then that is the predominant factor which affects the pH after the neutralization reaction is complete. Now, it's completely different when we use weak acids and weak bases. So once again, I'm going to keep saying this, but when we deal with weak acids or weak bases, we do the stoichiometry first. And that is when we assume that the reaction goes to completion. Strong acids push the equilibrium to the product side. Strong bases push the equilibrium to the product side. So in doing that, we add our strong acid, reacts with our weak base. We're just simply increasing then the amount of weak acid that's present. Or we add a strong base, which reacts with our weak acid. And that is just going to increase the concentration of our weak base that is present. And we have that ratio then of moles of our weak acid to moles of our weak base, because both of them are present in the solution. So because both of them are present in the solution, one on the reactant side, one on the product side, then it becomes an equilibrium problem. So this point, we've done our ice table up here. We do our ice table to see how many moles of our weak acid and weak base we have. And then we use the Henderson-Hasselbalch equation to calculate the pH. So if you go back to slides, I guess, what is that, 12 and 13, we can look at the difference in titration curves between strong acid, strong base. And here we're first looking at the titration of a weak acid, acetic acid, with a strong base, sodium hydroxide. So it takes a lot longer. We see a much more gradual change in our pH as we add our sodium hydroxide. Our slope here, when we're reaching up to the equivalence point, is not nearly as close to being a vertical line as what it is with strong acid, strong base. What else do we notice? Well, when we have a weak acid and we're adding a strong base, our equivalence point is no longer neutral, but our pH is basic. And in this particular titration, our pH is 9.0. So our equivalence point is here. But the same way, after we've reached our equivalence point, we have no more acid to absorb the base. So then after this point, the only thing that is changing the pH is continual addition of that strong base. So the pH here relies solely on how much base we have added. As we go along here, right, our weak acid is reacting with our strong base. So we're only seeing a slight increase in our pH until we get closer and closer to the equivalence point. Now, there is something interesting about doing titrations with weak acids or weak bases, and that is what we call the halfway equivalence point. And when we reach the halfway equivalence point, your pH actually will equal your pKa. So the pKa for acetic acid, I want to say it's 4.74. It's either 4.74 or 4.94. I can't remember off the top of my head. So your pH will equal your pKa at your halfway equivalence point. At your equivalence point, it is determined then by looking at an ice table and setting it up in the way that we did with calculating pHs of salt solutions. So we started with an acid, but then at this point, the only thing that is in solution, we have converted all of our weak acid into conjugate base. And then that conjugate base can react with water. We would set up an equilibrium expression using Kb and solving them. So we start initially, pH here, 3.0. That is a Ka problem. What is it? How does acetic acid react with water? That is the only thing that is present. That determines the pH initially. Then we do stoichiometry to see how are we affecting the ratio of HA to A minus all through here, except for this special point where pH equals pKa. All through here, Henderson-Hasselbalch, once we reach the equivalence point, it is we have converted everything into conjugate base. So we would set up an ice table, calculate a Kb, use the equilibrium expression, find our pH that way. After this point, it is only determined, the pH is only determined by the amount of base that is present. So it all comes down to looking at calculating the number of moles of respective base that we have added. How does that affect our ratio? And then looking at specific concentrations once we have passed our equivalence point. So this slide here just looks at the different titration curves for these various Ka values. So as we decrease our Ka values, how do our titration curves change? Well, strong acid, we've seen that. So very, very small increase in the pH, and then we get this vertical line heading up to where we've passed our equivalence point and only our base matters. So the closer you are to being a strong acid, the more similar your curve is. But notice here, Ka of 10 to the negative 10, that's actually closer to being a base than anything. We start at a pH of about 6.5. So notice we increase, very gradual slope then when we actually reach the equivalence point. So this titration curve, instead of being a weak acid titrated with a strong base, now we are titrating a weak base with a strong acid. So initially, our pH looks like it's approximately 11. The pH here is determined only by your ammonium, or not ammonium, ammonia that is in solution. 0.05 molar ammonia, set up an ice table, equilibrium expression with Kb, solve for OH minus. That's how we get this pH. Now, after the initial point, once we've actually started adding, because right here we haven't added any acid. After we start adding acid, now we are affecting the ratio of weak base, weak acid in the solution. That ratio, because the conjugate acid of ammonia is the ammonium ion, NH3 to NH3+. So as we add HCl, we continue to convert NH3 into NH3+. The more acid we add, the more NH4, I think I said NH3+, NH4+. The more ammonium ion we produce, the more HCl that we add. So this is what's increasing. The ammonium ion increases because we are removing this weak base from solution. Base plus acid gives us water and salt. So our pH is continually decreasing. Why is it decreasing? Because we're adding acid. Adding acid means that the pH should go down. So once again, we can hit our halfway equivalence point, which is pH equals pKa, even though here we're dealing with a base, so we would be starting with kBs, but we know that we can find Ka from Kw. Keep that in mind. So everything we learned in the last chapter applies now. So we continue to decrease our pH until we reach the equivalence point. At the equivalence point, what has happened? We have converted all of our ammonia. I believe it's 5 millimoles. All of our ammonia has been converted into the ammonium ion. So at this point, the only thing that is in solution that can control the pH is the ammonium ion. Whatever concentration that is, we set up an ice table, find the Ka, equilibrium expression, solve for H3O+, we calculate a pH. Anything past this point, the only thing then that is determining the pH is how many more moles of HCl have we added. And keep in mind at the equivalence point, it's not concentration, it's number of moles, right? Moles comes from multiplying volume times molarity. So initially, it's an ice table using the Kb. Everything through here is using Henderson-Hasselbalch, except for that special point, which we call the halfway equivalence point, pH equals pKa. At the equivalence point, it is only the conjugate that is in solution that can react to determine the pH. After the equivalence point, it's looking at how many extra moles of acid are left over, and that is what determines the pH. We are going to do these problems of solving titrations of weak acids and weak bases. They are long, they are arduous, you won't like it, and that's just the way that it is. But you will start to see a pattern. We have already calculated, we already know how to calculate an initial pH of a weak acid or a weak base in solution. And we learned last chapter, we already know how to calculate the conjugate, because that's what we did in calculating salts. What is the pH of the conjugate in solution? So it's this middle part here that is really the new thing that we are learning and using the Henderson-Hasselbalch. Stoichiometry first, equilibrium second. And it's going to be so much fun. Okay, so on to the second part of this chapter, which deals with solubility equilibria and solubility products. So this is just a fancy way of looking at precipitation reactions. That is what a solubility product equilibrium constant tells us. So at equilibrium, this means that there is a certain amount of solid that is dissolving into solution at the same rate that the ions are forming a solid and precipitating out. That is equilibrium. We have to be going both ways. Solid becoming ions, ions becoming solid. So notice this is basically the exact reverse way of how we write a net ionic equation for a precipitation reaction. If you don't remember how to do that, you can refer back to chapter 7 in our textbook. So solubility is an equilibrium position. And usually we write KSP, we write equilibrium expressions for solids that are only partially soluble or highly insoluble in water. And once again, our K values are always given with a specific temperature, because we know that generally speaking, if we increase the temperature, we can increase the solubility of a solid into a liquid. So this is our solubility equilibrium expression. So we always have the solid as the reactant and your ions as the product. And just as within the last chapter in looking at equilibria, we can write an equilibrium expression. And notice, because the solid is our reactant, you will never have a denominator, because we do not include solids or liquids in our equilibrium expressions. We only include aqueous. So we would have Bi3 plus squared times S2 minus cubed. So here we have our KSP. So this is a constant which tells you how soluble is bismuth sulfide in a solution. Now, relative solubilities. If we are comparing solubilities of salts with the same number of ions. So here I have a list: silver bromide, nickel 2 carbonate, iron 2 sulfide. 1 to 1, 1 to 1, 1 to 1. So we have 2 ions that are soluble, or we're looking at 2 ions that are in this particular reaction. If we do this and we set up our equilibrium expression, this would be x times x, x times x, x times x. So we would have our KSP equals x squared. We can solve this. Those solubilities we can compare directly. So if our magnitudes are 10 to the negative 8, 10 to the negative 10, 10 to the negative 15. Well, what's more soluble? Something that's 10 to the negative 8 versus something 10 to the negative 15. Now, if we look at solubilities of salts with different number of ions, here barium fluoride, we get a total of 3 ions, silver hydroxide, 2 ions, strontium phosphate, 5 ions. We cannot just simply compare our KSP values. We actually have to solve for x, because here, this is x, and this would be 2x squared. So we'd end up with 4x cubed. This is x, this is x. That would be x squared. I'm just talking about what our equilibrium expression looks like. Here, we would have a 3x cubed and a 2x squared. That equilibrium expression would be 108 x to the 5th. So solving for x in these situations would be completely different versus when they are all the same number of ions dissolved, x squared, x squared, x squared. So you can compare solubilities when we have the same number of ions dissolved. KSP, straight up, what's bigger, what's smaller? If you have a different number of ions dissolved, you are actually going to have to solve for x and see which of those molar solubilities is larger. So we like to talk about things that affect solubility. What are some factors that affect solubility? What is the common ion effect? Common ion effect means that we already have one of those particular ions in solution. So if I go back a slide, what happens if I add silver bromide to a solution that already has bromide ions in it? Well, there's already a certain amount of bromide ions in it. Therefore, this would be less soluble because the solution can only hold as many ions as your solubility product tells us. So your solubility is not as great comparing just trying to dissolve a particular solid into water versus dissolving that solid into water that already has some of those ions present. So your solubility goes down. Now, pH is tricky. Two things that we can look at. We can either decrease the pH or increase the pH. Now, decreasing the pH means that we have an acidic environment if the anion is an effective base. So once again, my lovelies, you need to memorize your strong acids and strong bases. So an effective base means that the conjugate base came from a weak acid. Fluoride ion is a great example. The fluoride ion can react with H pluses, with protons or hydronium ions that are present, which means, excuse me, which means that the solubility would increase because you are effectively removing the fluoride ions from solution because they're doing a side reaction. F minus reacts with H plus. Because I've decreased the pH, I'm increasing the amount of H pluses of those protons that are present. I'm removing the F minus, so this is a Le Chatelier problem. If I remove a product, I increase the amount of products that are there. And looking at solubility, that means I'm going from a solid, which is my reactant, to the product, which are my ions. So I'm removing some ions, which means I can dissolve more of my reactant. So here I give an example, silver chloride versus silver phosphate. The Cl minus, That came from a strong acid. Hydrochloric acid, strong acid, HCl, breaks apart, never gets back together. Phosphate ion came from a 3-step dissociation of its protons because it started off as phosphoric acid, H3PO4, went down to the phosphate ion. So this was never a strong acid to begin with. Therefore, the PO4 3- can react with H pluses, which means this is getting pulled into a side reaction, which then allows more of this to dissolve. So comparing these, decreasing the pH, this has no effect because the chloride ion cannot react. No solubility change, same as in water. Here, though, we can dissolve more silver phosphate in an acidic solution than we can in a neutral solution because the phosphate ion acts as a base. Now, we can also look at what happens when we increase the pH, when we've added hydroxide ions. And that simply is just looking at then, can the cation that is present, and this is not a good example because we're using the same thing here, can the cation that is present form an insoluble precipitate with the hydroxide ion? I'm trying to think of a good example. For example, if I have iron chloride, or iron 3 chloride, sure, iron 3 chloride, iron 2 chloride, it doesn't matter. Iron in solution will form an insoluble precipitate with the hydroxide ion. You can form iron hydroxides. So if I put an iron chloride solution, iron chloride into a basic solution, I would see a higher solubility in a basic solution. If I have iron chloride, right, we just talked about the chloride ion, in a acidic solution, there's no effect. It does not increase the solubility because Cl- cannot act as an effective base. So the differences are, decrease the pH. We're looking at, can the anion act as a base? If we increase the pH, can the cation form an insoluble hydroxide precipitate? And I will give you a solubility rule sheet. You do not have to memorize what your soluble hydroxides are versus your insoluble hydroxides. Okay, so just in how we studied a QC, we can study Q as well in comparing it to KSP, and it works the same way. But now we call it an ion product constant, or an ion product, Q. So what happens if I mix two solutions? I have, let's see here, lead nitrate, and I mix it with sodium chloride. So lead nitrate plus sodium chloride. I'm going to form an insoluble precipitate of lead chloride. The sodium and the nitrate are spectator ions. Depending upon the concentrations and volumes that I add, calculating a number of moles here, will tell me, what is my Q value? Is Q greater than my KSP? Is Q greater than my solubility product constant? If so, I'm going to see a precipitation reaction. If Q is less than KSP, nothing happens. So it's a threshold. KSP is a threshold and says at this point, and some of these KSP values are extremely small, like 10 to the negative 20, 10 to the negative 30. Very small amount of ions will actually form a precipitation reaction. And this is really interesting because then we can look at, you could study your tap water, the water that comes out of your sink. What are the ions that are actually floating around in the water? You can add simple substances and do precipitation reactions to actually test the levels of lead or arsenic, excuse me, fluoride ion concentration, and fluoride's not necessarily bad, but your heavy metals, things like that. So selective precipitation. So we can look at precipitating out metal ions, and we do this based on what are things insoluble. When I add a particular solution, what will precipitate out? Some things don't precipitate out as chlorides. Some things just don't do that. Iron will not precipitate out with chloride. Iron will precipitate out if I have a basic solution, or I can precipitate out iron as a sulfide. Other things won't precipitate out. So here, for example, comparing barium to silver. Barium will not precipitate out if I add chloride ions, but silver will. I'll get silver chloride. It's a white solid. Barium chloride doesn't do anything. So it would leave the barium in solution. So qualitative analysis, and we did an experiment last semester with qualitative analysis where we tried to identify the lead, the mercury, or the silver that was present in your solution. So that is what qualitative analysis is. What is there? We don't care how much is there, just what is present. Amount, not important. Substances, what is it? That is important. So here is a table, or crap, I can't think of what the word is that I want to use. Flow chart. Flow chart of how we can precipitate out specific ions. So silver chloride, mercury chloride, lead chloride, these all react with chlorine, or the chloride ions. This is how we can precipitate out what we call group 1s, insoluble chlorides, out of these. These are all ions that could be present in a water sample. By adding our HCl, that leaves all of these other ions in solution. So what do we do next? We can add hydrosulfuric acid. So then what happens? We produce out any acid insoluble sulfides because you're adding acid. These are not soluble in the acid. So copper, bismuth, cadmium, lead, mercury, arsenic, antimony, and tin. Now notice we've actually already precipitated out our lead up here. However, this is the mercury 2 ion. This is the mercury 1 ion. Okay, so we can precipitate things out by adding the sulfide ion. What does that leave us with? Well, now we can make our solution basic. By creating a basic solution, now we're looking at what type of insoluble hydroxides are we forming? Base, insoluble sulfides, and hydroxides. So aluminum, iron 3, chromium 3, zinc, nickel, cobalt, manganese, and some iron. So we've got sulfides and hydroxides because some of these will still precipitate out. This was acid insoluble. Now we look at base insoluble. So what's left over? Some things that are not heavy metals and nasty stuff. So we add sodium carbonate. And once again, this carbonate ion is reacting as a weak base. So how does carbonate react? We can now pull out barium carbonate, calcium carbonate, and magnesium carbonate. And so this would be interesting because calcium in your water supply is one of those ions that actually contributes to being hard water. Iron is another one. Actually, magnesium is one that makes hard water, that creates those white residues around your sinks or your tubs or whatever it may be. That's what hard water is. These insoluble carbonates will come out in your water. So we can precipitate out barium, calcium, and magnesium, and that just leaves your alkali metal ions and ammonium, which these are always soluble. So there's not really a way to test the levels of, say, sodium, lithium, potassium, and ammonium in the water, because the only way you can really do that is a flame test. Dry out some water and get a Q-tip, rub it in whatever the salt residue is left over, and burn it. If it's a specific color, like it burns yellow, that means there's sodium present. If it burns pinkish or purple, it means there's potassium. So there are other tests that you can do, but those are not precipitation tests. So this is just, it's a neat way to, or it's a neat thing to think about in terms of how can we isolate certain heavy metals from each other if I have a water sample? How could I actually test to see what things are present in this water? So that's true for your water that you're drinking. It's true for lake water, for stream water, whatever it may be. This chemistry will always apply. So that concludes chapter 15. So what do we have? Buffer solutions, KSP. And I've talked extensively about both of these things. All I can tell you is to make sure that you are practicing ice tables, you are remembering how to set up equilibrium expressions, that you are keeping in mind how can we calculate pH. And with our KSP is making sure that we can write out a balanced equation for how do these solids separate into their respective ions, keeping coefficients in mind because those coefficients become exponents. And they're not one-to-one anymore, the way we saw with acids and bases. So read the chapter, do your homework problems, and good luck.